Okay, in this video I'm going to illustrate how you can utilize Stata's graphical user interface to carry out a confirmatory factor analysis and test a path analysis model using latent variables. Um, so I'm not going to go into all the bells and whistles associated with the program, but rather just to kind of give you a bird's eye view of different options that are available to you in terms of drawing and in terms of obtaining different outputs. So typically what you would do is you would either have data already in a Stata data file, or you might have to import data from another source into Stata, save the data as a Stata data file, and then basically you would perform whatever manipulations are necessary. So I'm not going to go into issues related to dealing with missing data or data screening and so forth. I'm going to mainly focus on the graphical user interface. But keep in mind that typically before you actually specify the model using the graphical user interface, you would want to do your data screening and save whatever changes to the data set that you actually make. So I'm going to start off by just importing some data from Excel into Stata. So I'm going to go to File, Import, and Excel Spreadsheet. I'll click on Browse, and this is the data file that I'm going to be working with. So this is a Microsoft Excel spreadsheet with the data, and so now I'm going to click on Open, and you'll see that basically I've got variable names, and these variable names. These are associated with different items on a questionnaire. So I have 3 items that are representing different constructs, and then the values for those items below. So I'm going to click on Import First Row as variable names, and then click on OK. So now I have the data imported into the Stata program, and I want to actually save the data file. Before we do that, I'm going to just show you that it actually exists. If you go to Data, Data Editor, go under Browse Mode, you can see that we have our variable names as well as the data associated with them. Under Browse Mode, you can't make any changes to the values in the data set. If you wanted to make any kind of changes, you would have to go into the data editor and go under the edit mode, and you can do that. But at any rate, I'm going to save this data file, this Stata data file. I'm just going to call this SEM, and it's going to be given a DTA file extension. So I'm going to click on Save, and so now I have the Stata data file that was created originally from the data in our Excel file. So to run our CFA and also run our path analysis using latent variables, what I'll need to do is to go to Statistics, SEM, and model building and estimation, and then this box is going to come up. If you get it if this box looks a lot smaller and you want more area, you can always go to View, and then you can say fit into the window, or zoom in and zoom out, or you can adjust the canvas size and so forth. But at any rate, so what I'm going to do is I am going to click on Add Observed Variables, and so I'm going to do this for, well, to tell you the truth, I'll just do this for each latent variable in the model. So I'm going to actually start with here, and so basically this is a little button right here. The rectangles are used for indicator or observed variables. The ovals are used for latent variables. So you can see as long as this button is pushed, as I put indicator variables into the interface, you can see these boxes continue to appear, and so I'm going to do this also on this side, since I'm going to have an outcome variable ultimately. So yeah, there we go. So now I want to click off of this button right here. So I'm going to just click Select, and so now nothing. I can't draw any more boxes at this point. If I wanted to draw more, I could certainly click back on here and do that, but I'm going to click off. So next I want to click on the oval, and this is to draw a latent variable. So I'm going to draw one here, I'm going to draw one down here, and then one here as well, and then click off. And next, so these are the indicator variables. These are based on the data in your data file, and these are basically going to be the latent factors. So next, what I'm going to do is I'm going to draw out the relationships between my latent variables and the latent and the or between the latent variables and the indicator variables. So I actually had 3 indicators per latent factor in my original model. So I'm going to draw this out. So you can see that we're using the single-headed arrow and drawing. And as we draw, we're going to get these uniqueness values on the left side of the indicator variables. So we're drawing those out. So basically, the uniqueness represents the variation in the indicator variables is not explained by the proposed latent factor. So there you go. So now I need to give names to each of these variables. So what I can do, I'm going to click off the path drawing part, and then I can click on a indicator variable or observed variable. And so when I do that, when it highlights, then this little line appears up here, and I can just basically use a little drop down and start to fill in. So I'm just going to highlight each of these and fill in. And these are the variable names from the original data set. Okay. So next, I need to give names to the latent variables. So when I highlight a latent variable up here where it says name, I'll just give it a name. So I'm just going to call this contact just generally, and then press enter, and there you go. It appears in the oval. For this one, I'm just going to call anxiety, and then press enter, and there you go. And then here, I'm just going to call this and then press enter, and there you go. So these are the latent constructs that are being used as that are used to explain variation in the original set of indicator variables. So if I want to draw out the frequently with CFA models, will allow the latent variables to be correlated. So I can use a little double-headed arrow here to add a covariance. So I'm going to just draw from here to here. So there's 1. Then from here to here, there's 2, and then from here to here, there's 3. So this is representing the covariances among the latent variables. So at this point, I'm just going to click off again and estimate the model. So if I go to estimation, press estimate, then I have different estimation methods. We're going to stick with maximum likelihood and use the standard default standard errors here, and I'm just going to press OK. And so now the model is being estimated. And so what we see in this particular case is the unstandardized solution. So you'll notice that one of the paths for each of these latent variables is fixed at 1. And basically, with the unstandardized solution, we have to give the latent variable a scale. So, and we can do this by fixing a path coefficient to 1. In the standardized solution, then basically there would not be paths that would be constrained to 1, and those paths would be estimated, but the variances of the latent variables would be fixed at 1. So right now we have the unstandardized solution, and you'll notice that if you click on a given path, then you'll get the unstandardized path coefficient as well as a test of significance of that path coefficient. So like for the unstandardized path coefficient from this latent variable to this variable here, it's -0.6, the z-value is -5.45, and the p-value is clearly going to be less than 0.05. So this would be a statistically significant path. So this indicator is significant as an indicator of this latent construct. We also have down below, we've got the standardized factor loadings as well. So this is a standardized factor loading between the latent variable and this particular indicator. And you can also see you have significance tests associated with those. You'll notice for this particular path right here, the unstandardized loading is 1.02. The significance level, it's indicating statistical significance. And then here's our standardized path coefficient, our factor loading as well. So you'd interpret really the standardized factor loading very much like you would interpret the factor loadings associated with exploratory factor analysis, where the loadings are expressed more in correlational terms, or at least when you're looking at the structure matrix where you don't have more of a complex factor model that's given. So you'll notice that for the paths that are fixed at 1, you'll see right here the regression coefficient was fixed at 1. So there's no standard error associated with it. So there's no test of this indicator as to see if it's a significant indicator of the latent construct, because basically the latent variable is being scaled in relation to that variable. The same would go over here. So you can see there's the fixed path coefficient or factor loading, and the standard error is 0 because that path is not being estimated. And the same would go right here. So in terms of looking at the associations among the latent variables, you can see that in the unstandardized solution you get covariances among the latent variables because, again, the latent variables are being scaled in relation to one of the indicator variables. If you look at the standardized solution, the covariance is actually the correlation between the latent variables. So it's expressed in Pearson correlation terms. So if you want this information in a little bit more compact form, you can go into the output file here, and you can see that we've got our factor loadings. So you've got the coefficients. These are the unstandardized loadings here. So you've got your coefficient. You can see that for this latent variable going to this particular indicator, the first of the indicators, the coefficient is fixed at 1 and it's constrained. So there's no test of significance of that particular path. From the latent variable to contact 2, there's the unstandardized factor loading, standard error, z-value, and then significance tests. Then we have the latent variable to contact 3. That factor loading is being estimated and tested. So that occurs for each of our indicator variables where the paths are not fixed at 1. So let's say we want to look at the global fit of the model. So we want to see how well overall our specification fits the data. So we can do this by going to Estimation, Goodness of Fit, and then click on Overall Goodness of Fit. And so typically I will just, under Statistics to be displayed, I'll click on All of the Above and then press OK. And so now when we go to our output file, you can see that we have a chi-square test, root mean square error of approximation, comparative fit index, Tucker-Lewis index, and standardized root mean residual. So with the chi-square test that we see right here, this is a p-value, and so what one indicator of a good model fit to the data is a non-significant chi-square test. So if we have a value that's less than 0.05, that would be indicating statistical significance, and that's actually a bad thing if we are assessing fit. So the chi-square test is oftentimes thought of as a badness of fit test, and if it's statistically significant, that would suggest that we have poor model fit to the data. So we can see right here for this particular test, the chi-square value is less than 0.05, which would suggest a poor model fit to the data. The downside of the chi-square test is that it is impacted by sample size, and so given that SEM procedures tend to be large sample procedures, it would be very easy to obtain statistical significance with a model that exhibits fair or acceptable fit in other ways. So so it's useful to assess other more descriptive indices like the RMSEA, or root mean square error of approximation. For this index, good fit is indicated by values that are 0.05 or below, acceptable at 0.08 or below, and so this index right here is falling at 0.08, which would be fairly acceptable. It's not great fit, but it's acceptable given that rule of thumb. When we look at the comparative fit index and the Tucker-Lewis index, good fit is indicated by values that would be at 0.90 or above. More optimal levels would be above 0.95 or above. And so you can see that using those rules of thumb, the CFI would be indicating at least an acceptable model fit, whereas the TLI would be indicating a poor or low model fit. The standardized root mean squared residual, a good model fit is indicated by values at 0.05 or below, and in this case, this index is falling. The value of this index is falling above 0.05. So we have sort of mixed evidence for model fit. The chi-square test is suggesting poor fit. The RMSEA is suggesting at least acceptable fit. Comparative fit index is consistent with an acceptable fitting model, but the Tucker-Lewis and the standardized root mean residual are suggestive of poor model fit. So we have sort of a mixed bag in this case, and that sometimes can happen. You can have different fit indices that can kind of suggest a different way of thinking about fit. But we can look at the different fit indices as sort of different lenses for assessing overall fit. If we want to look at, we can also look at fit in terms of equation level goodness of fit. So I'm going to click on this and click on OK. And so basically what's going to happen, or what has happened, is we get R-squared values for each of our indicator or observed variables in the model. And the R-squared values are basically communality estimates. So these are proportions of variation accounted for in the indicator variables by the latent factors that have been specified to predict those variables. So if we multiply these proportions by 100%, we can talk about them in percentage terms. So we could say that the latent variable associated with contact 1 accounts for about 68% of the variation in that indicator. It accounts for about 44% of the variation in contact 2 and 33% of the variation in contact 3. The anxiety variable accounts for about 46% of the variation in the first indicator, roughly 36% in the second, and so forth. So basically, we can also, in theory, ask for modification indices to sort of explore where we could possibly add parameters to improve model fit. So if we click on modification indices and click on OK, when we look at our output file, these are some suggested parameters that we could add to improve the overall model fit. The thing to keep in mind, though, is that modification indices are purely an empirical strategy for deciding on what parameters to add to the model, and so they may not necessarily be suggestive of, or they may not necessarily be consistent with theory. So that's, like I said, a very brief overview of running a CFA. Now I want to quickly illustrate just running just a path analysis using latent variables. So what I'm going to do is I'm actually going to get rid of these parameters. So I'm just highlighting this and pressing delete, highlighting this one and pressing delete, and highlighting this one and pressing delete. And in fact, I'm going to just kind of click off of show estimates here so that I can kind of clean it up a little bit. So in this particular case, I've got 3 latent variables, and I could have other latent variables where I could be specifying more complex path models, but for this particular illustration right here, I'm just going to stick with this basic design. So I'm going to use this arrow from this variable to this variable, And you can see that when I do this, an error term or a disturbance term is generated because this latent variable is basically a latent and endogenous variable, whereas these are being treated as exogenous. If I add in a covariance between these two variables here, then basically what this is nothing more than a regression analysis using latent variables as opposed to just indicator or observed variables. Like I said, I could add in another latent variable and make a more complex model. And in fact, why don't I just do this really quickly? I'll just add in okay, so here what I've just kind of I've added in another variable as well to make this a little bit more complex path model. So you can see that we've got these two latent variables predicting this variable, and only this variable predicting this one right here. Notice that we can move things around too if we highlight a given parameter, and just we can sort of drag it around and make things a little bit cleaner looking. To sort of improve the way our appearance of within the model. So at any rate, now that I've specified this particular path model, basically what we have is a direct effect here from this variable to this variable, a direct effect here, and then we also have a direct effect between this variable, and then an indirect effect via this route. So we'll click on estimation and estimate, and then click on OK. So the model is being estimated, and I want to go back and I want to show the estimates in the model. And so these are the estimates for the unstandardized solution. So if we click on this path right here, this would be interpreted as an unstandardized path coefficient. The standardized path coefficient is given below. You can see that both of these have the significance levels associated with them, but I would focus on interpreting the significance associated with the unstandardized path coefficient. So there's the path coefficient for this path here, both the unstandardized and standardized solutions, and so forth. So there we go. If we look in our output file, you can see that it kind of grows. That basically we've got the measurement model, which the measurement model is basically from the CFA, and then the structural component is basically laying out the paths and forming the relationships, predictive relationships among the latent variables. So basically from this variable to this variable right here, that path coefficient, the unstandardized path coefficient, is negative 0.026, and it was not statistically significant. There's your p-value, there's the z value associated with that test. This variable to this variable right here, there's your path coefficient, and that relationship was not statistically significant. When we go from anxiety to this outcome variable here, there's the coefficient, and you can see that that was statistically significant. So looking at those parameters in the model, basically what we have is the path from this variable to this latent variable is statistically significant in the model. If we want to look at overall model fit, we can go to goodness of fit, overall goodness of fit, leave it as all right here, and click on OK. And there we go. We've got our chi-square test. We can see that the chi-square test was statistically significant, suggesting poor model fit to the data. The RMSEA was at 0.05, which is at a preferred level and suggesting a good model fit. The CFI was at 0.972 and TLI 0.963. Both of these values were above 0.90, suggesting good fit. The SRMR was 0.057, which is a little bit above what we would conventionally consider good fit. So we have sort of a mixed bag suggesting related to the fit of the model. The RMSEA, the CFI, TLI are suggesting good fit. The chi-square test is suggesting poorer fit, as well as the SRMR. And then we can also look at the but when we look at the paths in the model, we actually see that really only one of those paths among the latent variables is statistically significant. If we want to look at the R-squared values associated with our latent variables, we can go to goodness of fit and equation level goodness of fit. And so we've got the R-squared values. So these are basically, again, the uniquenesses associated with each of our indicator variables in the model. And then we have the R-squared values associated with this variable is 0.162. So our predictors accounted for about 16.2% of the variation in this variable. But in terms of this variable right here, we basically account for less than 1% of the variation. So really, from at the equation level, we're not really doing a very good job of explaining variation in this variable right here based on this variable, but we are doing a fair job of explaining variation in this variable. But given that this path is the only one that's significant, the lion's share of the variation in this variable is largely accounted for by the anxiety variable. So at any rate, there are, we still have, we can look at modification indices to see if there's any other paths, see if there are any other paths that we might, or parameters that we might include that might improve the fit of the model to the data. So that's certainly an option. There's also, we can ask for, under estimation, we can ask for, direct and indirect effects. So we can click on this and basically get, when we just go with the default, what we end up with is, looking at when we're looking at the indirect effects, we want to consult the structural component when we're looking at the relationships among the latent variables. So, prejudice to this variable right here, there was no indirect path that was estimated. From contact to this variable, there was no indirect path, but from anxiety to that variable, there is. So, basically, as you can see, this variable to this variable, that's a direct effect, and then this variable to this variable via this prejudice variable is an indirect effect. So that's the only indirect effect that was tested in the model. So, at any rate, the point of this exercise was just basically, again, to illustrate how you can carry out a CFA and also a path analysis using latent variables in the Stata program. So, like I said, obviously I'm not going into a lot of depth in terms of interpreting various parameters, just because there are quite frankly a lot of them to look at. Just keep in mind that generally speaking, one of the prominent strategies that is utilized when testing a full path analysis with latent variables is you start off with a CFA or test basically a measurement model to see how well the indicator variables are representing their latent constructs. And then if that model fits the data well, then moving into laying out proposed causal associations among the latent variables. So, when I started this video, I focused mainly on these three latent variables right here. And then as I was kind of expanded the discussion into the path analytic part, I actually added this variable here with its latent variables. Ordinarily, I would have basically started off with a CFA model that would have incorporated all four of these latent variables in their respective indicators, test that out to see how well it fits the data, and if it did, then lay out the proposed causal associations. I didn't do that in this particular case, but that would be the ordinary strategy that one would utilize en route to testing the path analysis with the latent variables. So I hope you find this helpful as a discussion of how to use the GUI or GUI in the Stata program, and while you're running CFAs and testing path analysis models with latent variables.